then we can go to the last presentation for today, the introduction to markets by Jason Hansen. He is a senior research economist at INL. So, Jason, floor is yours.
Thank you, Aaron. Okay, well, good morning, everybody. Thank you for sticking around to hear the component on economics. As Aaron mentioned, I'm an economist here at the Idaho National Laboratory. And so in this presentation, I hope to give you a bit of a high-level overview of the economic environment in which these models are intended to run, and to basically think through some of the issues and think of it more at a high-level perspective and how those things can be reflected in the modeling capabilities. So I'd like to start off today with a nice picture of an electricity system. So, I mean, I'm sure this is not new to any of you, but I think it's helpful to set the stage for thinking about some of the challenges that we face today in terms of economics. And so there's primarily three different categories that are contributors to the electricity system. There's the, let me pull my pointer up here. There's the generation that we tend to talk a lot about, the generation of electricity and different assets for generation, and how those feed into the transmission network, how the voltage requirements to get ramped up to be able to go on a transmission grid, and how they move around from one region to another, and then they get stepped down into a distribution network, and then it's that distribution network that takes the electricity to the end users, whether they be residential customers or commercial customers or institutional customers, industrial customers, things of that nature. And so it's helpful to think about this for the following reason. I mean, essentially, this is the supply chain of electricity, and at each of these different stages, there are different technical and economic considerations that have to be dealt with. And so what I'm going to start off with in the first part of my talk today is thinking about the organizational structure of how those things are organized, particularly in terms of what we might think of as a centralized system versus a decentralized system. And I'm going to be a little bit more specific about centralized versus decentralized and call them vertically integrated regulated utilities versus restructured, deregulated, competitive entities in a competitive market. And so these are two different approaches for managing this system. Okay, and so that's what I'm going to highlight here at the first. So in terms of an overview of what I plan to talk about, I'm going to spend just a little bit of time talking about these vertically integrated utilities and what are their economic incentives. Paul mentioned these, he alluded to these earlier in his talk when he mentioned that largely the nuclear fleet that we have today was built under a structure of vertically integrated utilities. And so some of the difficulties that the nuclear fleet faces today are in response to this evolution from vertically integrated utilities to restructured, deregulated operations. And so I'm going to spend a little time talking about that. And then I'm also going to spend a little time talking about the U.S. wholesale electricity markets, where I'm going to talk a little bit about the two-settlement system, which you might have heard of as referred to as the day-ahead market and the real-time market. Also a little bit about ancillary services and capacity markets. But when I get into this portion right here, talking about the electricity markets, really it's managing this interface right here that we'll be talking about, okay? All right, so in terms of the vertically integrated utility, what does that mean? Well, in the vertically integrated system, there is a single ownership structure that covers the generation assets, the transmission assets, and also the distribution assets. And so when I say single owner, I don't mean to say that there's a single person necessarily. It can be a corporation or many different structures. But what I do mean is that it's a single corporation that's managing from the origination of the electrons all the way through to the consumption of the electrons. Okay, So a single sole provider. In economics, we call that a monopoly. And so there are some very particular things that have to be dealt with as we talk about a monopoly. And particularly with this type of monopoly, this is what's referred to as a natural monopoly. Now, before I get too far in this, I recognize that we have a broad, diverse audience. And so for some of you, this might be review, but for others, maybe this will be new information. And so hopefully this can be somewhat of a setting the stage and putting us all on the same page in terms of nomenclature and understanding the incentives that different entities face. So particularly with natural monopolies, that's the situation where there are large fixed costs. So you think about the infrastructure requirements to build generation assets, the infrastructure requirements to build transmission assets, and the infrastructure requirements to build distribution assets down into the households and communities where the electricity is consumed. If there was to be a competition of these assets, can just think for a moment about all of the infrastructure that would have to be in place. If there were multiple firms, you'd have to have transmission assets that belong to firm A, transmission assets that belong to firm B, etc. It'd be a waste of resources. And so the fact that there is a single set of infrastructure in place, that's what's referred to as a natural monopoly. So in economics, we refer to a monopoly pricing as a market failure. And so there's a need for a correction of the market failure. So how does that work? Well, if a monopolist chooses the price without any sort of regulation or any sort of intervention, they choose to operate where their marginal revenue intersects with their marginal cost. They produce Q1 units of production. Then they look up to the demand curve to see what the price is that the market will bear. And the green area represents what we might consider monopoly profits. Fair enough, straightforward. Well, because that's a market failure, that's not being the monopolist would not choose to operate in the most efficient manner. Regulation comes into play. And so for much of the 20th century in the United States, rate of return regulation is what governed the operation of that entire supply chain of electricity that I described on the previous slides. Okay, so what does rate of return regulation mean? Well, there's a couple of different components of it. The utility has to submit to a regulator. This is a state regulator. They have to submit to the state regulator what their expenses are. And then they also have to submit to their state regulator this SB component that I'm calling right there. So what that is that's essentially the rate base. What that represents is the amount of investment, excuse me, the amount of investment that the utility has incurred for its capital expenditures, and then it petitions to the regulator an allowance S of some rate of return on that capital. So in a rate case, the utility is negotiating with the state regulator this rate of return on allowable capital. They're also negotiating with the regulator which portion of their expenses can be attributed to the rate base versus which are simply just operational expenses of running the system. So the categorization of costs, that's part of the discussion in the rate case. And then also, once this is established, then there's a rate that's issued where the state regulator tells the utility, okay, you can charge a price P to your customers. And that price P has reflected in it some return on their capital. Okay, so you can think about, as the industry built up under this type of regime, the financial attractiveness that this would provide for financial investment. For example, imagine if you had savings and you're interested in investing in your portfolio, you're going to look for where there's secure assets. These utilities were extremely secure assets because they were guaranteed some particular rate of return, 10%, 12%, guaranteed by law in the state where they're operating. That made them extremely financially attractive investments, which allowed for the buildup of the industry to take place in a period with very lucrative financial arrangements, attractive interest rates, attractive financing mechanisms because of how attractive the return is for those who invested in these utilities. Okay, so that's one part of the story there. But then there's another part of the story, which is that these attractive investments and this guaranteed rate of return, and the fact that depending on the negotiations, there could be investment capital passed on to the rate base, in which the what we would call in economics perverse incentives. So, for example, in 1962, there were some researchers, Avrich and Johnson, which identified that it's actually that during this period of time, it was actually in the utility's best interest to incur additional costs, to incur additional capital expenditures, because that added to the rate base. And by adding to the rate base, the argument could be made that there was a need to pass on the rate increases to customers through prices. So that's one component of the perverse incentives that it created for the utilities to not necessarily be seeking the most cost-efficient build-up practices. So as Paul mentioned previously, the industry was built up under a different regime than is in place today. That's part of the regime that it was built up under, is this rate of return regulation. There's some additional perverse incentives that are created, and that is, one is what we refer to as regulatory capture, which means in many cases, the very regulators who were responsible for regulating these utilities in different states formerly were part of the utility industry. So there was this back and forth that created this paradigm of incentive structures that made it very cost effective for utilities to build up during this time. Okay, but then they're entered into a period where there started to be some changes that happened to this model. In the late 70s, in 1978, there was a regulation that was passed that allowed for independent system operators to become established. So no longer did an independent system operator have to be part of this large utility managing this whole infrastructure from generation to distribution. Now independent power producers could be built. And then later in the 90s, there was another law that was passed as part of the Energy Policy Act, which allowed for financial entities to buy and sell electricity. So these financial entities didn't even own generation assets or transmission assets or distribution, but yet they could buy and sell electricity as if it was a commodity, like pork bellies or oil or different commodities that you think of. And so that created an additional evolution in the regulatory structure that utilities were operating under. And then by the end of the 90s, early 2000s, the state of California and the state of Pennsylvania went to a full-on deregulated model where they disband this rate of return regulation style that I'm showing here, and they entered into a regime of a competitive allocation of resources. So meaning that the market and the market mechanisms would be used to allocate resources for the generation, transmission, and production of electricity. So then, along with that, that's about the time that the Federal Energy Regulatory Commission, FERC, enters in and says transmission ownership can no longer be held by a monopoly corporation, and independent power producers now have access to the transmission network. And so coming out of that is this deregulated model that much of the country, 2/3 of the country, operates in today. Okay, so in the deregulated model, how does that work? Well, so now generators, for the generation assets, the very first of the system that I showed in the previous slides, the generators have to bid into a market, into an electricity market, based on their marginal cost of production and their capacity. So say, for example, a generator with a cost structure that looks like this. This is a generator that has large fixed costs, declining average costs, and constant marginal costs. So they bid into the market what their marginal cost of production is, as well as their capacity, how much capacity they can provide to the market. Okay, well, those are the market rules under which they operate. So if they do that, now what do we see? Well, the generator bids in their marginal cost, which their short run marginal cost, which allows them to recover their variable cost of production, their fuel cost, operations and maintenance, things of that nature. But it does not, the marginal cost does not allow them to recover their average cost, where their average cost includes their investment capital and those large infrastructure investments that I spoke of previously. So for generators that have a constant marginal cost and a declining average cost curve of this nature, they incur losses for participating in a deregulated market. This is what we refer to as the missing money problem. So I'll come back to that in a few slides to talk about that more in detail. But the scale of this missing money problem is dependent on the cost structure of generators that bid into the market. So this is the case of large generators with constant marginal costs. So nuclear generator, for example, is one with large infrastructure fixed cost capital investments. And so this would be a representation of a nuclear utilities cost structure. Now, notice what happens if we look at the same structure, we look at the same deregulated cost structure, the same structure of bidding into the market, your marginal cost, but instead of having a constant marginal cost, now you have an increasing marginal cost. So this is the case of generators that are able to ramp up and be more flexible, like gas-powered plants or oil-producing peaker plants, things of that nature. So they have an increasing marginal cost. So when generators with an increasing marginal cost bid into the market, notice what changes in terms of their financial performance. Now they're not only able to cover, generators with increasing marginal costs, their bid allows them to not only cover all of their variable costs, but it allows them to cover their fixed costs also, which means that they're able to attain profits in that sort of a regime structure. So this is a characteristic of a firm, of a generator with increasing average cost, which simply means that a generator like this has relatively low fixed cost, but high variable cost. So it doesn't cost a lot to build a plant of this type of nature, but it costs a lot to operate the plant. And so those operational costs, those variable costs, are reflected more in their marginal cost than they are in the case of the generator with large fixed costs. And so it changes the paradigm. So the interesting thing about this is that generators like this with a cost structure that looks like this are in the same market competing against generators that have a cost structure that looks like this, which creates a competitive environment for this class of generators that's very difficult to compete in. Okay, so this portion of the marginal cost curve, where the generator in the case of high variable costs and low fixed costs, this portion of the curve represents what becomes their bid into a market. Okay, this marginal cost curve right there. Whereas for a generator of this class, their bid represents their marginal cost and their total amount of capacity. So this is the basis, this is the underlying theory of what's driving the bids that enter into the market. Okay. Oh, my slides are a little ahead of me. So these marginal cost curves get summed across all generators. So here's the marginal cost curve of the generator with the large fixed cost and low variable cost. Here's the marginal cost curve of the generator with low fixed costs and increasing marginal cost. This is their portion of the supply curve. And this supply curve right here is what we refer to as the bid stack. So a grid operator or a market operator receives these bids from the generators in their market and then determines the allocation of how these are going to be operated. But before we get into that, there's some terminology that I'd like to identify here. So the grid operator looks to see where their forecasted demand or their forecasted load intersects with their supply curve, and then the entity for whom their bid intersects the demand curve becomes what we call the marginal generator, or in other words, this is the clearing price that enters the market. And we typically refer to those in our industry as the locational marginal prices. So that's how they are, that's where they come from. Okay, so, and this is happening as been mentioned in our modeling exercises at every moment of the day. Okay, so we refer to this in economics as producer surplus, as the difference between the price that clears the market versus the marginal cost that a generator receives. And so for those generators that have large fixed costs, their producer surplus would be producer surplus A, and those generators that have low fixed cost but high variable cost, their producer surplus would be surplus B. So producer surplus should not be confused with profits. Profits is simply that we take the producer surplus, the per unit profitability, multiply it across all the units of production, and then we have to subtract off the fixed costs. Okay, so that sounds well and good. That sounds like there shouldn't be a missing money problem. So why is it the case? Well, this producer surplus, there's dynamics that happen in the market which cause this producer surplus to be insufficient to cover the fixed costs of these very large capital intensive generators that I mentioned previously. So say, for example, what's the impact of a production tax credit, or changing prices for natural gas, or carbon tax? So how that works is that the production tax credit, like different asset generation technologies, might receive a production tax credit from the government to produce, regardless of what their cost structure is. So long as they are producing, that allows them to be part of the market and enter a bid into the market. That's going to change the position of this supply curve, which in turn will change the producer surplus for the remaining generators who are in the market who do not receive the production tax credit. So that's one element of dynamics that impacts generators. Another one has to do with the changing prices for natural gas. So a natural gas turbine is an increasing marginal cost generator. So as the price of natural gas changes, this portion of the supply curve actually flattens out. And in the process of flattening out, it reduces this producer surplus, again affecting the profitability of large fixed cost generators that are in the market. A carbon tax, we don't have a carbon tax yet, but if a carbon tax goes into effect, then that's going to shift the supply curve for all of the generators that are clean producers, which will change the nature of their producer surplus also. So I set this out just as an illustration that this is the mechanism that's now used in deregulated markets. Okay, so how do deregulated markets expand across the US? There are some pockets of the country where deregulation has not taken place. So for example, in the Southeast, in the Southwest, and in the Northwest, these parts of the country continue to operate in a regulated market regime. Whereas these others, the PJM, for example, others that we commonly talk about in our modeling exercises, these are part of the deregulated market structure. Okay, and the important thing to note, the reason that I provide that little bit of historical context is that this is a management style that is in flux. Okay, for most of the 20th century, the deregulated regime is what governed electricity generation across all of the United States. This deregulated regime is scarcely 20 years old, 2 decades. We have very little experience with it, and so it's a market in evolution, and so things will continue to adjust. But the important feature about that for our purposes is that the functions of balancing load, of regulating frequency, and of expanding capacity that formerly was accomplished from the purview of a single entity looking over the entire supply chain, now we have market forces that are governing all of these different components in these deregulated markets. And so that change in dynamics, the fact that we're now in a competitive environment, changes the incentives that different firms operate under, and so the nature of the game has fundamentally changed. So this market structure that I've presented previously now is the allocation mechanism, the market allocation mechanism, which governs these markets that I'm going to talk about. So now we enter into what we refer to as the two settlement system. Why do we refer to that as the two settlement system? Well, these generators that I mentioned, they enter a bid for production into the day ahead market. So 24 hours out from when production will be needed, generators enter their bids into the market according to what I just described previously. And the grid operator and the market operator at the level of the regional transmission authority, which is this map right there, the grid operator receives those bids and they have a projection of demand. And so they allocate, or in other words, they schedule generators to operate 24 hours out from now. Okay, so generators receive their instructions for how much capacity they need to produce in the next 24 hours from now. And the prices that clear those markets are what are referred to as locational marginal prices. Locational because in a network that spans across these electricity markets that I showed on the previous slide, there's nodes where these electricity prices are being calculated. So the generators enter their bids, the operator receives their bids and schedules with the generators how much they need to produce, and the generator sees what they anticipate as being their locational marginal price that they'll get from producing electricity at that time. So that's settlement one. But you can imagine that in the next 24 hours, there's still uncertainty involved that Paul mentioned in his talk with stochasticity. There's uncertainty with respect to our forecast on load. The load or our demand, it may change from what we originally had used to schedule our generators. There may be changes in the supply characteristics. Maybe it's going to be a sunny day and we'll have a lot of variable renewables, or maybe we anticipated to have a lot of variable renewables, but then there's a cloud cover that comes across and the wind's not blowing, and so now we've got a supply shortage. So in other words, there's noise or there's uncertainty in the estimates of the day ahead market. And so because of that, the real-time market is the second settlement point. And so again, the generators on a much shorter time frame now are submitting their bids for, say, 1 hour from now, or maybe 15 minutes from now, or maybe even 5 minutes from now. They're submitting their bids saying, I can provide electricity in the next 5 minutes, and this is how much capacity I can use. So the real-time market is used to settle the noise left over from the day ahead market. And again, there are locational marginal prices that are computed, and those are distributed across the grid network of where the utility, where the independent system operator is managing the system. Okay, but yet there's still noise, there's still uncertainty, there's still stochasticity at the level below the 5-minute market, below the 15 market, below the hour market. In the UK, they refer to this as the tea kettle phenomenon, or maybe in the United States, everybody suddenly turns on their TV to watch the Super Bowl. Well, if that happens at a time frame less than what was forecasted in the real-time market, there's still error, there's still noise that has to be accounted for. That's the role of the ancillary services market. Okay, the ancillary services are those services that the grid operator can call what the real-time market operates at. The first one being the reserve market, where the generator can where the operator can call upon generators who are currently spinning, and they can either ramp up or ramp down as needed to make those load adjustments. They can also call upon generators that are not spinning, so long as the generator has the ability to turn on the asset within a short amount of time, in 10 minutes, 5 minutes, 30 minutes, it depends across different markets that you're looking at. So this is the adjustment market for the level below what the real-time market settles out. Okay. All right, but then there's additionally the regulation market, which deals with the frequency control. So the quality of the electricity really matters also, and there's an economic component to this as well. So the quality component being that the grid has to be maintained at 60 hertz, and so that frequency has to be maintained. And so when a consumer plugs in their iPhone or their computer or whatever, it changes the voltage that's on the system. So that's constantly in balance and has to be balanced across across the system. So instead of the market operator calling on the generator in a bid fashion, for these regulation reserves, there's actually sensors that are put on the generators. And so in an instantaneous fashion, the grid operator can ramp up or ramp down the generation assets that have selected to be part of the frequency control market. Okay, so there's a little bit about the physics of how that works. I'm gonna, in the interest of time, I'm gonna skip over these two additional slides on ancillary services so that I can get to the capacity market. So I mentioned previously the missing money problem. I characterized what that is. So grid operators recognize that they need generators to be financially solvent. They need generators to be around to provide electricity. And so a capacity market was established to try to cover what we refer to as the missing money problem. Okay, so how the capacity market works is, again, generators are bidding into a market, but now they're bidding into a market to provide services for 3 months out, or to provide services for 3 years out, to have capacity online and available. And so that's a method of stability that the grid operator can use to make sure that they have capacity to operate their system X amount of time out from now. And across all of these markets, there's a little bit of variation in how markets operate, the capacity market, how they operate the ancillary services market. For example, the CAISO in California doesn't use a capacity market. They use what's referred to as a resource adequacy market, but they're all essentially trying to solve this missing money problem that large fixed cost generators face. And so in the capacity market, the grid operator sets what's referred to as the gross cone, or in other words, the cone represents the cost of new entrant. And so this is typically set as the highest cost generator that can operate in that market. And so generator bids have to come in less than that. And the bids that the generators submit is what's referred to as the net cone. Okay, so you can think of the net cone as being the monetary equivalent of the missing money problem for each generator. So a nuclear generator is going to submit a bid for a net cone that's going to be different than a natural gas generator, which will be different than a wind power generator, for example. So this net cone is the capacity bid that each of the generators are going to submit to the market. And then the grid operator is going to look to see what percentage of additional capacity do they want to have online. And so they, in some markets, they have a downward sloping demand curve like this. This is actually from PJM. But in some markets, they have a vertical demand curve, which just simply means we need X amount of capacity, and we're going to pay the same price for all of the capacity that we acquire. So there, as I mentioned, there's a little bit of variation in that. So in terms of how the energy market in the two settlement system varies from the capacity market and the ancillary services market, this data comes from a study that EPRI did for us a few years ago, and you can see that there's significant differences in volume of the electricity market. What's that, about $6 billion on the low end, up to about nearly $30 billion on the high end in PJM. That's compared to the capacity market has value that ranges from 3.6 million up to 3.6 billion up to 11 billion in the capacity market, et cetera, for the ancillary services market. So there's variation in value that's attainable in those different markets. So to summarize, the points that I want to leave you with is that there are significant modeling differences related to the economic performance of a regulated utility versus a deregulated utility. The shape of, or the assumptions about, marginal cost significantly matter to the firm's profitability, particularly because we have large fixed cost generators who are competing against entities that are large variable cost generators. That plays on the economics at the level of the firm. In the restructured markets, a competitive market model is used to allocate these different functions that formerly was accomplished by a regulated utility managing across the entire supply chain of the utility. And then finally, the market for ancillary services and capacity provide additional values for utilities, although not as strong as the electricity market itself. And so, Aaron, with that, I'm a little bit over time, but I'm concluding there.
Thank you very much, Jason. It's always good to see market overviews as a non-economist, right? So thank you again. The connection here is, so these all these markets, as Paul said, can be modeled in our force tools. So all that what Jason was talking about is input to our force tools. So we cannot do forecasts of markets as well, capacity expansion as Paul said, but we use capacity expansion models and all what Jason said here, how these different market structures they can be modeled in our force tools. So those are inputs. There is one question I see in the chat which says, and Paul answered, but anyways, he says in some of the ISOs I see sometimes negative pricing. What does that mean, and how does that work?
Yeah, that's an excellent question. So negative pricing. So I mentioned previously in the slides, I mentioned the production tax credit. So some generators receive a subsidy program provided by the government because they're a clean energy generating technology. And so that subsidy program requires the generator to participate in the market if they want to receive the subsidy. So they may or may not have a cost. They may, in order to participate in the market, to guarantee them a place in the market, they might submit a bid with a negative price. And they submit that bid with a negative price because it ensures them the ability to collect the subsidy for clean energy from the government. So that's where we see rise of negative prices. And that supply curve that I showed, it adjusts that supply curve up and down because of those subsidies that some generators get versus other generators.
Okay, thank you. There is one more question. Thank you for the presentation from Askin. Does the marginal cost curve estimate profit with assumptions of transmission or distribution lines being reliable? So is there some reliability component baked in?
To the extent that it connects to the grid, I'm not sure about how that works. The marginal cost assumptions that I was going over would be from the perspective of the generator themselves. And so they have to participate in the transmission network. And so that would be a cost that the transmission owner would be responsible for. In some cases, the owner of the generation asset may or may not be the owner of the transmission asset. So I guess I don't have a really solid answer on that. From my perspective, I've just been looking at it from the perspective of the generator.
Perfect, thank you. I see Dayo has his hand raised.
Yes, thank you very. Can you?
Yes, we can hear you.
Hear me? Yeah, thank you very much, Jason, for what I think is an excellent exploration of the economics behind power systems. The question I have for you is related to what happened in Texas early last year when temperatures suddenly fell and there was excessive demand for heat. And that led to a collapse of the entire, infrastructure. The question to you is, you did mention something about the frequency, the need to maintain the frequency of 60 hertz due to increases in demand and volatilities in supply. So the question here is, in your opinion, what do you think was the single most important factor for the breakdown of the system in Texas last year? Thank you.
Yeah, that's an excellent question. So the simple answer would be there's correlated risks. So that would be my simple one-line answer. But a little bit more involved answer is that in Texas, ERCOT chooses not to use what's referred to as these capacity markets that I mentioned. Instead, ERCOT uses what is called scarcity pricing to try to incentivize capacity. So the idea with scarcity pricing is that every once in a while, the electricity prices get sufficiently high to incentivize new generation from coming online. Well, that works so long as the scarcity prices bring generation assets on, and then people can pay those scarcity prices. So that's part of the issue that was dealt with in Texas. An additional issue that was dealt with in Texas is the difficulty in transmission. The network is somewhat isolated. In fact, it is isolated with very few connection points to an external grid. And that was done intentionally to try to subvert regulations so that there was not a need to be regulated by federal authorities. Well, that means that in the event of a catastrophe like what Texas faced, they don't have access to those external networks that were surrounding their state. So there's a lot that goes into that, the answer to your question. My simple answer is that there are correlated risks, but as I've alluded to, some of the market structure, the way the ERCOT model is set up, was part and parcel to some of the difficulties that they faced in Texas.
Thank you very much, Jason.
Thank you, Jason. And I think, oh, there's one more. We have time. We have time for a couple more. Another interesting variable would be energy storage, batteries, hydrogen, etc. Any insight on how it would affect the energy market and its prices?
So that's an element of capacity expansion that we haven't, as previously mentioned, our force tools, we don't look explicitly at capacity expansion. And capacity expansion in general, for the models that are out there, that's actually an area where capacity expansion needs to improve. So what I mean by improve, what I mean by that is, as batteries come online, as the hydrogen market becomes more viable, that's most definitely going to impact the economics in the electricity market. There will be dynamics as the hydrogen market takes off, as batteries become more viable, that's going to change the economic performance of the markets as they operate today. That's a part of capacity expansion that, in my humble economic opinion, is a vulnerability that we've not really entered into yet, but is an area that we need to expand upon.
Perfect. Yeah, you generate much more questions than the technical presentations before. So there's one more from another guest. Are the costs assumed to be deterministic? Because prices can be set, but costs not. If costs are uncertain, how is that taken into account in regulated and deregulated markets?
So the cost structure, I mean, the cost to operate a generator, whether it's in a regulated market or in a deregulated market, it's going to be the same. The cost structure, that aspect of it is not going to change. What's going to change is the revenue side of it. So on the regulated side, there's this guaranteed rate of return that is that is used as a matter of cost, estimating return based on the cost. Whereas in the deregulated market, the generator has to submit their marginal cost bid. So one thing that is related to your question is that there is a literature that has examined what happened to nuclear generators going from a deregulated market regime, going from a regulated market regime to a deregulated market regime. And in fact, some of the research is suggesting that nuclear generators have improved in their efficiency, so that actually this participation in a competitive market required generators to become more efficient. So there's evidence in the literature that provides context on that. There's another element that this deregulated market space has, because of the cost efficiency, because of the need for cost efficiency, it has incurred a wave of mergers and acquisitions. So now utilities have actually gotten much larger. You know, they've acquired more assets to try to spread their costs out over a larger base of distribution so that they can be more competitive. So those are a couple of different components of how costs have adjusted in the migration from a regulatory structure to a deregulated nature.
Thank you. And we are soon at the top of the hour here. I see one more question, and I think we can take this. So in your graphs, you assume the demand to be inelastic. Is there ambition to model somewhat elastic demand at longer timescales?
This is a really excellent question. So one of the things that is in the literature says that part of the problem that electricity markets are facing today is that we are using short-term signals to try to inform long-term investments. So we're using short-run marginal cost. Even the capacity market, where capacity markets exist, those are still relatively short-term decisions, 3 months out or 3 years out. Instead, we should be thinking about the longer-term prices and the signals that we get out of the longer-term markets, which would imply more elastic supply curves, and more elastic demand curves. That over time, there's more elasticity over time than there is in the near term. But yet, our thinking and our analysis tends to focus on these short-term signals to try to inform long-term decisions. And so that's part of the disconnect or yeah, the disconnect in long-term planning is that those signals are not being sent.
Perfect. Hey, thank you very much again, Jason. I think that was the last question I see coming through. And with that, that was the last presentation of the first module of this overview and training. So this was more the overview portion of it, and I hope this produced some interest in learning more and how to use the tools. So you're, as mentioned, all the tools are open source. You're welcome and invited to download them and check them out before the next sessions. And the next sessions will then drill deeper into each of the tools and how to use them. So the next module is tomorrow morning. I hope to see you all there, where we will talk about the teal and farm components, and then again get some insights in how to visualize results, get more details on the demonstration cases, and get an overview of our experimental program. And then next week, as mentioned, the full day Heron and the full day hybrid trainings on Wednesday and Thursday. So I hope to see you all tomorrow morning, and with that, have a good rest of your day. Thank you very much.